Imagine measuring the movement of an entire tectonic plate and detecting only a few millimeters of motion per year, or monitoring a bridge, a dam, or a landslide with extraordinary precision. At first glance, that sounds impossible. Yet scientists and engineers do it every day using a technique called Static GNSS. But how can a GNSS receiver measure positions with millimeter-level precision? And what actually happens behind the scenes? Static GNSS is one of the most accurate positioning methods available today. Unlike real-time techniques such as RTK, Static GNSS is based on collecting raw satellite observations over an extended period of time. Instead of providing an immediate position solution, the receiver continuously records measurements from multiple satellites. The collected data is then processed later using specialized software. This approach requires patience, but it can produce extremely accurate results. One of the most common questions is, why do static surveys often last for hours? The answer lies in the nature of GNSS measurements. Satellite signals are affected by many sources of uncertainty, including atmospheric conditions, satellite geometry, and measurement noise. By observing satellites for longer periods, more information becomes available. As satellites move across the sky, their geometry changes, helping improve the quality and reliability of the final solution. Longer observation sessions generally allow many of these uncertainties to be reduced more effectively. Once field observations are completed, the real work begins. The raw GNSS data is transferred to processing software where numerous error sources are modeled and corrected. Atmospheric delays caused by the ionosphere and troposphere must be considered. Satellite and receiver clock errors must be accounted for. Orbital information must be incorporated. To eliminate common errors, geodesists use mathematical techniques known as differencing. These include single differences, double differences, and even triple differences. While the mathematics can become quite sophisticated, the goal is simple: remove as much error as possible from the observations. The remarkable accuracy of static GNSS comes from combining long observation periods with rigorous data processing. Under favorable conditions, millimeter-level precision can be achieved. However, accuracy is never determined by a single factor. It depends on many variables: baseline length between stations, observation duration, satellite visibility, receiver and antenna quality, environmental conditions, and even the processing strategy itself. This is why experienced surveyors and geodesists carefully design observation campaigns before collecting data. Because of its exceptional accuracy, Static GNSS is widely used in applications where precision is critical. National geodetic control networks are often established using static observations. Scientists use Static GNSS to monitor tectonic plate motion and study crustal deformation. The technique is also used for monitoring dams, bridges, buildings, mines, landslides, and other structures where even small movements can be significant. In many scientific applications, Static GNSS provides measurements that simply cannot be achieved with faster positioning methods. For many engineering and surveying projects, commercial GNSS processing software provides excellent results. However, when studying tectonic motion across hundreds or even thousands of kilometers, additional challenges emerge. At these scales, advanced scientific software packages are often required. Systems such as Gamut/GlobeK, Bernese GNSS software, and GypsyX are widely used within the scientific community. These tools incorporate sophisticated atmospheric models and advanced estimation techniques designed for high-precision geodetic applications. Their purpose is not simply to compute coordinates. Their purpose is to reveal tiny motions occurring across the Earth's surface. Static GNSS is not the fastest positioning method. It is not designed to provide instant results, and it requires careful observation and processing. But when the highest possible accuracy is required, Static GNSS remains one of the most powerful tools available to surveyors, engineers, and scientists. From national reference networks to tectonic monitoring and deformation analysis, it continues to play a fundamental role in modern geodesy. In future videos, we'll explore GNSS processing, RTK, PPP, and geodetic monitoring techniques in much greater detail. Subscribe to GeoGMon and turn on notifications so you don't miss future videos about GNSS, Earth monitoring, and geospatial technologies.